Pascal's principle. Basically, every time I think of Pascal's principle, the first thing I think about is a tube of toothpaste. Because basically what Pascal was saying is, if you push down and increase the pressure at one point of a closed container, that increase in pressure is going to be felt throughout the whole container. You know, it's going to be felt right here on the cap. And basically, if that cap is open, then the toothpaste would end up coming out. So basically, here's the official Pascal's principle. If there is a change in pressure at any point in a container, then this change in pressure is felt equally throughout all walls of the container. Squeeze the toothpaste over here. The toothpaste pushes harder against that closed lid. And when the lid is open, you squeeze harder over here. That increase in pressure oozes the toothpaste on out. Another thing I think about is a hydraulic jack. I remember, using these on my dad's farm to raise up a wagon, change a flat tire, and basically, like, the jack would be sitting here on the ground, and you put it underneath, some sort of structure. Maybe it was a wagon. This is obviously not drawn to scale. Person here. So that's not a wagon, that's something else. But anyway, basically, you put this handle in here, and when you exert a force down on the handle, basically, there's a little piston here that pushes down, and this is all like one container of hydraulic oil. And basically, before we were looking at the tube of toothpaste, now we're looking at a container of oil, and here's all the oil in here, yes? And basically, if you put a force down here and exert an increase in pressure over there, that increase in pressure is going to be felt along all of the walls of the container, yes? And this wall of the container isn't fixed. It's a movable piston. So what ends up happening is that increase in pressure ends up pushing this piston up, and you end up raising the hay wagon or whatever you're trying to raise. Let's look at a more textbook type situation. Here is our jack. Here's our closed container. Filled with hydraulic oil. And what we're going to do is exert a downward force, F1, over here. And this little area right in there is A1. And that increase in pressure is going to cause a force over here, F2, to be exerted on that area, A2. Now let's give some numbers here. Let's say you exert a downward force over here of 10 newtons. And let's say that this little tiny area, the little piston area over there, let's say it's a small area of 3.14 times 10 to the negative fourth meter squared. And let's say that this area over here is, let's make it a little bit bigger. (3.14) times 10 to the negative second. So basically what Pascal is saying is that the pressure is going to be the same at both these locations, especially here, because they're at the same altitude. If we look at this problem over here, it's going to be a little bit more complicated because the one piston here is at a higher altitude than the lower one here. But at first, this first problem here, the pressure here at 1 is same as the pressure at 2. Same depth. Therefore, pressure is equal to force divided by area. So the force exerted down on the point 1, that surface area over there, area 1, is going to equal to the upward force exerted on area 2. But check this out. I take my little 10 Newton force and I exert it on that smaller little area. And let's see how much we can actually lift up here, this F2. And that's how, a guy like me could lift up this whole big, heavy, wagon. I'm just exerting a little force of 10 newtons, and basically I can lift up 1,000 Newton, wagon. And sometimes those areas are even at a greater ratio. And if you add in this little height factor right here, that even gives you a little bit more of an advantage. Let's check out that lower problem. Let me get rid of some of this stuff here. Okay, so this is a whole different problem altogether. So you know what I'm going to do? I'm just going to just wipe this whole thing out here. Okay, I think we're finally ready here to analyze this situation here. So let's say that basically, let's say that this car right here has a weight of 20,500 newtons. And this here is solid metal here. But basically, this all here is the chamber with the hydraulic oil in it. And let's say that this up here is area 1, this down here is area 2, and let's get some values for that. Area 1 here is 0.0120 meters, and area 2 here is much bigger area, 0.150, but this is meters squared. And the question is, how much force would I have to exert down on the jack to raise up this car, which weighs 20,500 newtons? But there's one more factor that makes this problem a little bit more difficult than the last one, and that is this depth factor. And the metal part of the jack here that floats up and down there, that's at a lower depth. And let's say that this H right there is 1.10 meters. Alrighty. So here's the deal. Since the pressure here and the pressure here are at the same depth, basically we could think of this point and this point as being like one and the same in terms of like pressure. So you know what? I'm going to call this point C. I'm going to call this point B. I'm going to call this point up here A. Okay. And basically the pressure at point B is going to be equal to the pressure at point C because the fluid is at the same depth. Yes? Now, if I start off with my depth equation saying, look, the pressure at the lower point equals the pressure at the higher point plus rho GH, yes? I can make a substitution here and I could say, look, the pressure at the lower point is going to be the pressure at B. The pressure at the higher point would be the pressure at A. And let me make some room here. Plus my rho GH. However, I know that the pressure at B is the same as the pressure at C. So basically, the pressure at C is going to equal the pressure at A plus rho GH. And now I'm going to come back up top here. The pressure at C would be the force at C over the area at C. The pressure at A would be the force exerted at A over the area at A plus rho GH. Now, what is this force at C? Well, force at C right here, that particular point right there, we want that force to be the weight of the car because that's what we have to lift up. So we want this upward force, at point C to be the weight of the car. So what was that weight? $20,500 newtons. All over the area over there, which is 0.150 meters squared. And that's going to equal the force at A. Well, that's the thing we're trying to figure out. How much would I have to push that piston down there over the area at A, which is going to be 0.012 meters, plus, let me make some room here, well, the density would be the density of the hydraulic oil. So basically, the density of the hydraulic oil, that's given in the problem. Let's see, what is that density? 8 times 10 to the second. So over here, the rho GH term, it's going to be 8 times 10 to the negative second kilogram meters cubed times 10 meters per second squared times the depth, 1.10 meters. And now we just solve for that one unknown, the force at A. Yeah, that's a positive. Yep. $1,530 newtons, which is a heck of a lot less than 20,500 newtons. All right, look, in summary, Pascal's principle. If you got a closed container and you're considering 2 points that are at the same depth, okay, basically you could just say the pressure at one point is going to equal the pressure at the other point. If you're considering 2 points at different depths, well, we know that the pressure here is going to equal the pressure here, and then this depth here is going to be the same. So you have to also bring into that depth formula P2 equals P1 plus rho GH.